Okay, so we will talk about another block cipher, which is data encryption standard. So, this is basically a 64-bit block cipher, 64-bit. So, plain text and ciphertext size are 64-bit, and this is a 16 round block cipher. So, R is 16. Okay. So, the history of this block cipher is basically, can you please go to the slide? Yeah. So, it is a 16 round fistal cipher, we will come to that what is fistal cipher, and the plain text and ciphertext is 64-bit, and DES is most widely used encryption scheme adopted in 1977 by NIST, and they made this as a standard. And this is historically DES is from the cipher which is called Louis cipher, which is designed by IBM in 16th, and this was they have modified this slightly and then it became a DES. So, basically it is a 16 round block cipher. So, we have a plain text which is 64-bit, and we have 16 rounds. So, F1, F2, then F16, and for each round, as we know, we need another input which are called round key. So, we have 16 round keys, and this is the and this round keys is coming from key scheduling algorithm, which is taking the key, the secret key shared between Alice and Bob, and giving the round keys, okay, and getting this is the ciphertext. So, this is a typical 16 round block cipher, and this is also 64-bit. Plain text and ciphertext are 64-bit. So, this is DES encryption, and we have to talk about the round function encryption. This is the general structure of the DES encryption. We have 16 round, and for each round we have two input. One is the first round input is the plain text, and last round output is the ciphertext. Okay. And for each round we need to have the round keys Ks, and these are coming from the key scheduling algorithm, which we have to we need to talk what is the key scheduling algorithm for DES. And DES round function are basically what is called fistal cipher. Fistal structure, fistal cipher. So, it is a 64-bit plain text. So, we denote this L0 R0. This is a one round fistal structure, and it will output L1 R1. So, this R0 is directly copied here, and for this part we have to apply a function f, which is taking input as R0 and the round key. You can say K1 for first round key, and it is bitwise XORing with this and giving us the R1. So, basically we have this L1 is the R0 and R1 is basically f of R0 comma K1 XOR with L0. So, this is the input, this is the output. So, this is a typical one round fistal cipher. So, DES is basically each round of DES is basically this function, this fistal function. It is just dividing the 64-bit plain text into two parts, 32-bit, 32-bit, and this 32-bit is directly copied here, and this 32 bit we are taking the input of a function f, which is having another input which is the round key, which is 48 bit, and this is 32 bit. So, this f has two input 32 bit and 48 bit, and it is giving us output 32 bit again, and this 32 bit output we are XORing with the left part of the plain text, and we are getting the bitwise XORing, and then we are getting the right part of this output R1. So, this is a one round DES or one round Feastel cipher. So, the DES rounds are basically this Feastel, okay, and this round keys is basically 42 bit. Now, how to get this round key? We will talk about the key scheduling algorithm from the secret key, how we are getting the round keys. Okay, so, let us just write the full description of the DES. So, each round is a Feastel structure, and so basically we have the plain text x, which we denote by x0. This is the plain text. Okay. So, it is a 64 bit. So, what we are doing? We are breaking into this into two part. No, yeah. So, first this is a 64 bit. So, we are applying a permutation on it, which we denoted by IP. So, this is a permutation which is taking 64 bit input, and it is again giving us a 64 bit output. This is a permutation. We will talk about, we will see what is this permutation is. So, then this 64 bit we are now dividing into two part, 32 bit, 32 bit. This is L0 R0, and then we are applying the Feastel cipher. So, this part is directly copied here. This is L1 R1, and then this part we are applying a function f, which is taking input k1, the round function. This is 48 bits, and this is 32 bit, and this we are XORing with bitwise XORing with this, and we are getting this L0 R0. Now, again we will this is the first round function of the DES. So, in the first round we have a one extra operation which is called permutation operation. We are just suppling the bits, we are just changing the position of the bits, random suppling. So, what is this IP? We will come in a moment. So, this is first round F1. Then after that again we have to apply the second round. So, second round is basically, so again it is a Feastel cipher. So, again it will, so this is L2 R2. So, this will copied here. So, this will apply the same f function, and this is the K2 second round function, and this will XOR with this, this will this. So, this way will continue. So, again we have another Feastel cipher. So, this way will continue dot dot dot, finally we reach to L16 R16. Okay. So, finally, we reach to L16 R16. So, after reaching to L16 R16, so L16 R16. So, these are many, these are 15 more Feastel cipher, 15 round. This is one round, first round, then we have 15 round of this. Okay. After that, what we do? We will apply the inverse permutation of IP inverse. We have a IP, then we will apply the IP inverse, and then we will get the ciphertext. This is 64 bit, this is Y, this is ciphertext. Okay. So, for here we have need to have K16. So, for each, so we have K1, K2, K16 round function, each round keys, and each round keys is a 48 bit. Okay. So, now we will see what is this IP. So, can you please go to the slide? Yeah. So, this is the IP. So, IP is basically, so we have the this plain text. So, plain texts are basically x1, x2, x3, x4 like x64. Okay. Now, this on this we want to apply this IP. IP means we are supplying the bits. So, how we are supplying? We are supplying by this. So, this will so x58 will come here, then x50, then x42, then x34, then x26, then x18, x10, x2, then x60 like this. So, it is basically, so x56 is coming here, x2 is going there. So, supplying of the bits. Can you please go to the slide? So, this is the way we are supplying. So, x56 will come here, then x58, then x50 like this, x2, then x60 like this. So, we are just supplying the bits, and this is the inverse permutation of this permutation, and this we are going to apply in the after this 16 round of the DES. So, this is just the IP inverse. So, inverse of this permutation. Okay. So, now we will talk about this f function, because we have used this f function here. So, this is a typical DES encryption. We have to talk about decryption also. So, let us just talk about the f function, because we have used f function here. So, f has two input. So, DES f function. Okay. Okay. So, it has two input, one is 32 bit, we denote this by say A, and another one is the key, say K1 for the first round. Okay, this is 48 bit and this is 32 bit. So, what we are going to do? We want to XOR this bitwise XOR, but these are two different size. So, we cannot do the bitwise XOR unless we do something, unless we expand this or unless we reduce this. So, better to expand this. So, we will apply a expansion function on this to make it this is 32 bit to make it 48 bit, and then this is also 48 bit. Now, we can easily bitwise XOR these two and we get a 48 bit output. Okay. Now, this 48 bit output will divide into 6 bit blocks. So, how many blocks will be there? So, this is 48 bit. So, we will divide into 6 bit blocks. So, this is a B1, B2, B3, B4, B5, B6, B7, B8. So, each of BI is a 6 bit, each of BI is 6 bit. So, we just divide into 6 bit blocks, because we want to apply S box which is taking input 6 bit and giving output 4 bit. Now, suppose we have some S box, say S1, which is taking input 6 bit 1, 2, 3, 4, 5, 6 and giving output 4 bit. We have another S box S2, which is again taking input this B2 6 bit giving 4 bit, like this 6 bit S3, S4, S5, S6, S7, S8. Okay, so these SIs are basically the substitution function, which are S box basically. So, SI is basically taking a 6-bit input and giving us the 4-bit output. So, I is equal to 1, 2, 3, 4, 5, 6, 7, 8. We have such 8 S boxes. Okay. So, how they will look like, we will come to know. So, each of this is a 6-bit, we are applying this S box and we are getting 4-bit output. So, 4-bit output. Okay. So, then what we do, then this is total is 32-bit. Then we apply a permutation on this 32-bit, which is denoted by P, again supplying the bits, and then this is the output of f a comma k 1. So, this is the f function. So, this is again 32-bit. So, this is 32-bit. So, it is just P is the random I mean the one permutation which is taking 32-bit, giving us the 32-bit. Okay. So, this is typical f function of this DES Feastel cipher. So, now we have to know what are this expansion function and the S box. Okay. So, this is the expansion function. So, we have a 32-bit number. So, from this 32-bit we want to make it 48 bits. So, some number has to be repeated. So, say for example, 4 is repeated. So, this is how many rows? 1, 2, 3, 4, 5, 6, 7, 8. How many columns? 1, 2, 3, 4, 5, 6. So, this is a 48-bit number. So, we just apply this expansion function. So, if our so we are applying expansion function over here. If our A is say A1, A2, A32. So, by that expansion function it is telling this will be A32, then A1, then A2, A3, A4, A5, then A4 again like this. So, this will be again 48 bits, and this is given by this matrix. This is a 8 by 6 matrix. So, this is again 48 bits. So, basically we are repeating some of the bits. 4 has repeated over here, 8 has repeated like this, 9 has repeated, 13 has repeated. So, many bits, because we have only 32 bit, we want to make it 48 bit. So, we have to repeat the bits. Okay. So, this is the expansion function. Now, we need to talk about the S box. Okay. So, S box, it is taking so this is a typical S box S1. So, basically each of this S box is taking 6-bit input and 4-bit output. So, if you denote this by x0, x1, x2, x3, x4, x5. Okay. So, this is say S1 we are talking about, say. So, now this x0 and x5. So, suppose we have a table of size so we have a matrix. So, this is 0, 1, 2, 3. So, 4 by 16 matrix. Okay. So, this is 0, 1, 2 up to 15 if you start from 0. Okay. Okay. Now, x and each of these entries is in hexadecimal form, because output is 4-bit. So, 4-bit can be represented in hex form. So, each of these entries is in hexadecimal form. So, now, suppose we want to get the output for this x0 to x5. So, x0 x5 will give us the row number. and this x1, x2, x3, x4, this will give us the column number of this matrix. Okay. Suppose this is I and this is say j. So, we will go to that particular. So, this is say j and this is say I. We will go to that particular position and we will get the value over there, that is in hexadecimal form, and that will be the output. Okay. Now, for example, for S1, suppose we want to get the output of this, say 1 0 1 0 1 1, say we want to get what is the output of this, what is the output of S1 if the input is this. So, these 2 bit will denote the row number. So, 1 1 means 3. So, this row. So, this is our I, third row, and these bits, this is basically 0 1 1 0. So, this is basically 4 and then plus 1 5. So, this is basically 5th. So, we have to go to the, so say this is 5th, say for example, we have to go to the this position and we have to get the value. So, can you go to the slide please? Yeah. So, this is the S box, it is giving in this form 0 1 this. So, we are looking for 5th third row and the 5th column. So, this is the this 0 9 is the S box we are looking for, the output of is output we are looking for. Okay. So, 9 is the output. So, 9 means what? 9 is basically 0 sorry 8 1 0 0 1. So, basically 1 0 0 1 is the output of this S box of this value, this value. So, this is how we have to read this S box from the table. So, there are 8 S box. Can you please go to the slide? So, there are 8 S box. This is the first S block, S1, S2, then we have the remaining S boxes like this. So, these are given in the table. So, designer just, there is no explanation how they are getting this S box, but they are just giving this S box by this table or by this matrix. So, this is one of the drawback of this DES. Now, come to the last permutation function in the that F. Okay. So, if you remember, so this is A. So, we are still in the F function. So, we are breaking it into, we are applying the S box, then this is the S box S1 S2, then this is 32 bit, and then we are applying a permutation P. Okay. So, this permutation is given in this table. So, this is the this is again a 32 bit number will be again 32 bit number. So, this is given by this. So, we have 16. So, S1 is going to here. So, S16 is coming in the font, then S7 is coming in the next. So, this is just a shuffling of the bits like this. So, this is our P permutation. Okay. So, this is the F function of the DES, one round DES, which is the Fistel cipher. Now, we talk about the key scheduling algorithm. So, how we can get the round keys from this secret key K. So, that is called key scheduling for DES. Okay. So, for key scheduling So, our key is actually the DES key size is, this is plain text size, this is the ciphertext size, and this is the key size. Okay. So, key size is typically, effective key size is 56 bit, but usually keys are given in 64 bits. So, if we look at this slide, keys are given in 64 bit, K1, K2, K3, K4, K5, K6, K7, K8, K9 like this, but these are the bits we use for the parity checking to detect the any error in the communication or not. So, these are not included in the key. So, effective key is other than this parity check bit. So, these bits are basically effective key bit, and this is 56 bit. So, if you just so this is our effective key, which is 56 bit, and these are the bits is usually come for the parity checking. So, this we ignore when we take the key. Okay. So, now, so we have key is 56 bit. So, we take this 56 bit key, secret key, and we divide into two parts. Okay. Then we apply a permutation which is called PC1. So, so 56 bit means this is 28 bit, 28 bit. So, total is 56 bit. So, we apply a permutation on this. So, we don't partition first, this is a 56 bit number, 56 bit key, effective key. So, we apply a permutation, just a sapling, and it will be again a 56 bit output. We will come to that what is a PC1. Okay. Now, we divide into two part, this is C0, D0, and each is 20. So, 56 bit, 28 bit, each of this is 28 bit. Okay. Now, we will apply circular shift, left circular shift on separately on both this part. Okay. This is for the first round key, we want to get first round key. Then we store it into what is called C1 D1, and then on this C1 D1 we apply another permutation PC2, and this will give us the K1. Okay. And to get K2, what we do? So, we have C1 D1. So, again we apply the circular shift, left circular shift. So, this is basically left circular shift, and it is either one time or two times depending on which round key we are looking for. Okay. So, it is a circular shift, left circular shift, but either one time or two time. Now, we will come to that. So, now if we just after this we will store it into what is called C2 D2, and we apply the same function PC2, and we get K2. So, like this we continue, and finally, we get K16. We need to have 16 round keys. So, okay. So, now we need to know what is the this PC1 and PC2. So, PC1 is basically taking effective key 56 bit. So, this is the keys alpha 1, alpha 2, alpha 7, alpha 8 is not there, because alpha 8 is just a parity check bit, alpha 9 like this. Okay. So, let us go to the what is the PC1. So, PC1 is given in this table. So, it is taking it is just a random sampling of the this 56 bit number, but we this is the, but we are removing the parity check bit, those are basically not the effective key. So, this is the PC1 we are having, and then in the PC2, and this is the round, this is the left shift we are doing. Here we are doing the left circular shift for each of this. Now, this is for the first round. So, first round we will do one times, For the second round also we will do one time, but for the third round, fourth round, fifth round, this round we will do twice circular shift. So, these are the number of times we will do circular shift, we are in which round, depending on that we will do this many circle, either one times or two times, depending on which round keys we are looking for. And this is basically typically PC2. PC2 is basically taking, so this is a input is basically again 56 bit, but the output is 48 bit. Okay. So, that means we need to remove some of the bits. So, this is the way how we are removing the sum of the bits. Please go to the slide. So, this is PC2. So, this is basically not taking all the bits. So, this is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. So, this is a 6 cross 8 matrix. So, there are 48 numbers. So, this is the way how we get this permutation from this 56 bit to 48 bit. So, this is basically alpha, I mean the 14 bit, this is 17 bit like this. So, 28 bit, then 15 bit. So, some of the bits are must be missing here, because we want to from 56 bit we want to make it to 48 bit. Okay. So, this is the overall diagram of this DES algorithm. This is the encryption algorithm. So, for encryption, so we are applying the first permutation, then we are having the first round function. These are all round function are basically Feastel cipher, and then for each round function we need to have this round key, and these round keys are basically coming from the key scheduling algorithm which we have discussed. And then finally, we have the after the 16 round we are applying the inverse permutation of this, and we are getting the ciphertext. So, this is the plain text, this is the ciphertext. Okay. So, this is the DES encryption. Now, in the next log we will talk about DES decryption, how we can decrypt the DES. Thank you.